I called this applications of magnetic forces. This really should be called just a few of the many, 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 many applications. But here are some neat ones. So I'd like you to consider an electron as follows. Now, this electron is traveling to the right. Do our right-hand rules work for electrons? No. So an electron traveling to the right is the same as a proton traveling which way? Okay, and it is hitting an external magnetic field. What are those X's meant to represent? What direction is the magnetic field? Oh, always someone that shows up late, right when I hit record. So we have an electron traveling to the right. That's the same as a proton traveling left. It's hitting an external magnetic field. What direction is this magnetic field? So let's all of us use my whiteboard behind me as our screen. So all of you point your right thumbs to the left, magnetic field into the page. Right when this electron hits the magnetic field, which way will it be deflected? Okay, so it's going to do this. It's going to travel freely, but right when it hits here, it's going to get deflected down. So now it's traveling that way, down and right. An electron traveling down and right is the same as a proton traveling which way? What's the opposite of down? Up and left. So everybody point your thumbs up and left, fingers into the page. Now which way will the electron get deflected? Kind of diagonally. And in fact, what we have is this. The electron will be forced into a circle. Do you know what that means we can say? We can say magnetic force is pushing me in a circle. No. Oh, yes! This is wonderful. This is going to allow us to build particle accelerators, and this is going to explain why particle accelerators are always circular. This. Have you ever wondered why the Large Hadron Collider, big rounds, why they make it a circle? This. So what do we have? What was the force on a single charge from a magnetic field? This is the one that we did last day. So somebody look at your formula sheet. This is not a current carrying wire. What was the force on a charge? What was the equation for the force on a charge? So you're looking for an F equals, and it's going to have the symbol for charge in it. That's how you know it's the equation for the force on a charge. I'm not going to move on until someone comes up with it, and a lot of you really need to be doing the homework. Yeah. Of course it's QVB. So we're going to have this. QVB equals mv squared over r. One of the v's is going to cancel because if I divide the left-hand v over, I would have a v squared on the top and a single v on the bottom. I have qb equals mv over r. This is one of the methods that we use to figure out what particles are being emitted when we smash them into each other. What we have here is 1, 2, 3, 4, 5 variables. If you give me 4, I can find the fifth. And usually in a particle accelerator, we know 4 of them because we've set it up that way. I like example 2. I like example 2. Example 2 is a nice question. An electron, it's an electron, moving at 3.2 times 10 to the 7th meters per second, enters a perpendicular magnetic field and traces out a circular path. What kind of a path, Oliver? That means I can say magnetic force is what's pushing me in a circle. Oliver, what's the magnetic force on a charge, on a moving charge? What's the equation? What's the equation for the magnetic force on a charge? The equation? QVB equals, circular motion, mv squared over r. How did I know to use the v one? Because I've got a v over here. That's why I didn't use the one with the period in it. And Alejandro, one of the v's cancels. Yay. Oliver, what are they asking me to find? Okay, now what we could do, we could observe the radius and we could solve for the magnitude of the charge or the mass of the object. So this is a very, very powerful tool we have when we're looking at particle physics. Where is the r right now, Oliver? On the, yeah! Wait a minute. Dividing by r on the right is the same as what? Where? Yeah. In other words, I can times the r to there. How would I move the q and the b over? So you're telling me that the radius, the m and the v are going to stay on top, and the q, sure. That's how I would get the r by itself. And now we're good to go. M, it's an electron, Oliver. This is why you all have your formula sheets out. Good, yeah, 9.11 times 10 to the negative 31. V, that's the speed. I scrolled down. What was it? 3.2 times 10 to the... divided by Q. It's an electron. It's fairly elementary to figure out the charge on an electron. It's a pretty elementary process. Oliver, what's the charge on an electron? Don't bail him out, Gerard. What's the charge on an electron? Good. Magnetic field B, what was that? The question told me, but I can't remember. Times 10 to the negative what? Good. What radius will this electron trace out? Good question. I'm going to need brackets around the top, definitely. Oh, I got a typo. Insert. Did you get 0.334? Yeah. Units? Meters. So there's a 0.3 of a meter. Yeah, it would trace out a radius, you know what, about the size of a ruler. I think rulers are 30 centimeters long. This is 33 centimeters. Thus the diameter would be twice as big, right? Again, as far as I'm concerned, for a charge hitting a external magnetic field, and it'll almost certainly be a proton or an electron, you've got the mass and the charge for both. I can give you any four of those concepts, and you can get the fifth one by itself. So example 3, as shown in the above diagram, this is from the January 1990 provincial exam. Oh, I graduated in 87, so I almost wrote this one. A proton, it's a proton. Entered a magnetic field at location A. The radius of the path was 3.25 meters. When the magnetic field strength was that, what was the proton's speed when it entered the magnetic field at location A? Sean, what's this asking me to find? Keep reading. Keep reading. What's it asking me to find? Speed. Okay. Look at the picture or look at the description. This is a charge being bent into a shape that starts with the letter C. This is a charge being bent into a shape that starts with the letter C and rhymes with Urkel. Okay. So what can we say? Magnetic force is what's pushing us in a circle. You're zoning out. I'm bringing you back. What's my equation for magnetic force on a moving charge, right from my formula sheet? I hate you. Yeah, QVB. And then it's going to be, don't forget the M, V squared over R. That's right from our circular motion unit. Ooh, one of the V's, Sean, cancels because if I divide the left V over, I'd have a V squared over V. What are they asking me to find? Oh, how would I get the V? How will I move the M over? What's the M doing to the V here? Okay, how will I move the R over? So yet another equation. You're telling me QBR over M, that equals V? I agree. Okay. Q, it's a proton. As I always say, it's a fairly elementary concept. What is it? Times 10 to the negative 19. Good. B, oh, they told me in the question, you know what? I'm going to write 0.02 instead of writing it in scientific notation because that's less typing. That's what 2 times 10 to negative 2 is. Radius, 3.25 meters. Divided by, Sean, mass of a proton on your sheet. It also, I think, starts with 1.6 times 10 to the... Good. What do you get? How fast was this proton travel? Shouldn't be going faster than the speed of light, though, but it'll be moving. 1 I can't type. 1.6 scientific notation, negative 19 times 0.02. Oh, that worked out evenly, which is a total fluke, but we'll take that. Did you get 600, 6 million, 6.5 times 10 to the 6th? Is that right? Okay, I got to type it. 1.6, 3.25. Oh, I missed the 7 on the bottom. There we go. I was going, how can that work out evenly? Because 1.67, that's pretty sure that's a prime number. There we go. That there, 6 point, so what do we have? 1, 2, 3, 4, 5, 6. 6.23 times 10 to the 6th. And that's going to be meters per second. Put your pencils down, look up. Come on, computer, you got this. Thank you. There we go.
This syringe contains a radioactive form of glucose known as FDG. The doctor will soon inject its contents into her patient's arm, whom she's testing for cancer using a PET scanner. The FDG will quickly circulate through his body. If he has a tumor, cancer cells within it will take up a significant portion of the FDG, which will act as a beacon for the scanner. PET tracers such as FDG are among the most remarkable tools in medical diagnostics, and their life begins in a particle accelerator, just hours earlier. The particle accelerator in question is called a cyclotron, and it's often housed in a bunker within hospitals. It uses electromagnetic fields to propel charged particles like protons faster and faster along a spiraling path. When the protons reach their maximum speed, they shoot out onto a target. That contains a few milliliters of a type of water with a heavy form of oxygen called oxygen 18. When a proton slams into one of these heavier oxygen atoms, it kicks out another subatomic particle called a neutron. This impact turns oxygen 18 into fluorine 18, a radioactive isotope that can be detected on a PET scan. In a little under 2 hours, about half the fluorine will be gone due to radioactive decay, so the clock is ticking to get the scan done. So how can fluorine 18 be used to detect diseases? Radiochemists at the hospital can use a series of chemical reactions to attach the radioactive fluorine to different molecules, creating radiotracers. The identity of the tracer depends on what doctors want to observe. FDG is a common one because the rate at which cells consume glucose can signal the presence of cancer, the location of an infection, or the slowing brain function of dementia. The FDG is now ready for the patient's scan. When a radio-labeled tracer enters the body, it travels through the circulatory system and gets taken up by its target, whether that's a protein in the brain, cancer cells, or otherwise. Within a few minutes, a significant amount of the tracer has found its way to the target area, and the rest has cleared from circulation. Now the doctors can see their target using a PET, or positron emission tomography, scanner. The radiation that the tracer emits is what makes this possible. The isotopes used in PET decay by positron emission. Positrons are essentially electrons with positive charge. When emitted, a positron collides with an electron from another molecule in its surroundings. This causes a tiny nuclear reaction in which the mass of the two particles is converted into two high-energy photons, similar to X-rays, that shoot out in opposite directions. These photons will then impact an array of paired radiation detectors in the scanner walls. The software in the scanner uses those detectors to estimate where inside the body the collision occurred and create a 3D map of the tracer's distribution. PET scans can detect the spread of cancer before it can be spotted with other types of imaging. They're also revolutionizing the diagnosis of Alzheimer's disease by allowing doctors to see amyloid, the telltale protein buildup that otherwise couldn't be confirmed without an autopsy. Meanwhile, researchers are actively working to develop new tracers and expand the possibilities of what PET scans can be used for. But with all this talk of radiation and nuclear reactions inside the body, are these scans safe? Even though no amount of ionizing radiation is completely safe, the amount of radiation the body receives during a PET scan is actually quite low. One scan is comparable to what you're exposed to over 2 or 3 years from natural radioactive sources, like radon gas, or the amount a pilot would rack up from cosmic radiation after 20 to 30 transatlantic flights. Most patients feel that those risks are acceptable for the chance to diagnose and treat their illnesses. If you think scanning the human body is as fascinating as we do, check out this lesson. Otherwise, here's a playlist on other fascinating technologies that'll spark your curiosity.
So no playlist, but that is very cutting edge, Sean. That's from 2019. I think it was in 2019. I was at a physics seminar, and a prof, I think from UBC, was showing us this technology, and he showed us a before and after. So the before picture was a patient suffering from pancreatic cancer, and his whole body was glowing. But now what they can do is because cancer cells use more glucose because they're growing faster, they eat more sugar than normal cells, they can tailor glucose molecules and they can put a cancer killer in it. And he showed us the after picture of this person that had a couple of tiny glowing dots, but most of their body was clear. That person was given 3 months to live, and nope, they were fine. They've gone into remission and they've lived a normal life. It's amazing what they can do. So one really cool application, particle accelerometers. What do I need to remember? Magnetic force is what's pulling me in a circle. And then, Sean, 5 variables. I'll ask you to get one of them by itself. I don't know what. Another very neat application is the electric motor. Suppose instead of a rigid wire in a straight line, let's suppose, Maya, we put a wire in a loop like this, and we put it in the magnetic field as shown below. Got another latecomer? Let me pause the video. So let's analyze this. First of all, let's look at this picture very carefully. I guess the current is going this way. And it looks like in section 1 it's going that way, in section 2 it's going that way. Draw this in, please. Section 3, section 4, back to section 1. And then once you've drawn that in, we're going to be using our right-hand rule quite a bit. This is the third one because I see an external magnetic field. Looks like the magnetic field is pointing to the right. Let's look at the chunk of wire that I've called chunk number 1. What direction will it feel a force? This one right here. you should find a problem. None. It's parallel to the magnetic field. So the direction of the force on segment one, and you can't bend your hand with the hi-fi hitchhiker one anyways. It doesn't work. But segment two, now let's use my board. It's going up the page. Magnetic field is pointing to the right. What direction will segment two feel a force? It's going to feel a force into the page. What about segment three? Segment three, not again because it's parallel, but segment four is going to feel a force which way? Point your right thumbs down. Yeah, you're going to find out of the page. And so what's going to happen? Now I'm going to use F for force, and I'm going to say on this side it's into the page, F for force, and on this side it's out of the page. This loop is going to spin a half turn. If you push down on one side of a loop and you lift up on the, did I get that right, Mr. Dueck? I got these backwards. Golly. My brain was twigging me. We said into the page for 2, yes? And we said out of the page for 4. If you push down, Maya, on one side of a loop and lift up, it'll flip a half turn. Now the problem is once it flips a half turn, well, then it would feel a force on this side out of the page because now 4 would be on the left and 2 would be on the right. So it would go flip, 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 which isn't what we want. We would like to see if we can get it to spin. So we're going to be clever. Okay. So first of all, will the loop tend to rotate? Yes. But only half a turn, and then it's going to flip back. How can we get it to spin? Because that's what a motor needs to do. A motor needs to be able to continue to spin to make tires turn or whatever. Well, we could reverse the field. We got more clever than that. We're going to use a completely physical system. So figure 7.28 shows a simple one-turn motor operated on direct current. You all want to turn the page, I think. Okay. You know what? Figure 7.28 has vanished, but I have figure 7.29. What we do, so here's a side view. Let's look at this motor here. Let's use mine as our analog, not your paper. So on the left-hand side, the current is moving this way, magnetic field into the to the right. The left side is going to get pushed down. The right side is going to get lifted up. It's going to spin. What we do is we put a gap right here so that the current actually can't go from this side to this side. And we use brushes right here. What happens, we call this a split ring commutator. What happens when it flips, it keeps the current always moving up on the left-hand side and always moving down on the right-hand side. It's tough to visualize. I have a lovely animation. It should say, yeah, here it is. Video, magnetic forces, and the DC, magnetic M for magnetic forces, and the DC motor. Mute the volume for now. So here's a nice example. I'll pause it several times, and then I'll show you the real thing. So you can see what we've done is we have a gap right here. This is called a split ring commutator. What we want to make sure is that here's the positive of the battery. Let me make this full size. Here's the positive of the battery, current going up. We always want the current right here going into the page. We always want the force on the right-hand side of this loop to be up. We always want the force on the left-hand side of this loop to be down. So let me start the motor.
The torque in a DC electric motor is created by magnetic forces exerted on the electric current carried by the rotating part of the motor. In this virtual model, the flow of conventional current is represented by the moving red balls. The magnetic field is represented by the blue lines.
That the current, the force on the left is always going to be pointing up. The force on the right, the force on the right is always up.
The current loop experiences a torque due to the offset forces on the top and bottom sections of the loop.
Now the only
forces on the front and back segments of the loop exactly cancel.
Shut the motor off right there. then there's no force to get it going. So modern motors, instead of having one loop, they have three at 120-degree angles. If you do it that way, no matter where the motor stops, there's always going to be a net force to get it to start to rotate and keep rotating. Now, right here, what we have are little brushes. Now, there are also motors that are called brushless motors that work similarly, but even more cleverly. We're not going to talk about those. But if you want to dive into the world, Gerard, of
So they do not
electric
contribute to
motors,
the
they're
net
pretty
torque on the
impressive.
loop.
But this here, this is like 19.
The battery that drives this motor produces a constant voltage which can only drive the current in one direction. However,
as long as it has enough momentum to skip the gap, the motor will turn, and I've got an upwards force on the right, a downwards force on the left. What if I want to flip it into reverse? I can flip the current, I can flip the magnetic field. I have lots of ways to make this go in reverse.
the motor loop would get stuck lined up perpendicular to the magnetic field if its current never changed direction. A clever
Got another one, I think, Mr. Dueck. What was it called? DC electric motor, letter D, Mr. Dueck. DC electric motor. So the same kind of an idea. Here is a split ring commutator. We have the current going from the battery that way. It means, again, to make sure that the current always runs on the correct side, Oliver, we have that commutator on the side like that, and they will gap. Basically, you can think of it as a hamburger bun with no patty, but a metal hamburger bun. Okay? Let me pause the video for a second. So this is also a nice application of the right-hand rule. This would be a nice right-hand rule multiple choicey question, giving you a picture of a motor and asking you which way is it going to spin? Which way will it turn? So here in this particular picture, I have current going into the page. Really, pen? I have current going into the page where the North Pole is right here. Come on. I have current going into the page right here. I have current coming out of the page right here. So if I point my thumb into the page, magnetic field that way, this is going to feel a force down. This is going to feel a force up. And then as it flips, I can just guarantee or continue to make sure with the split ring commutator that the current is always flowing into the page on the left. Or the other option is I can hook it up to alternating current, that I don't need the split ring commutator, but then the motor will turn at the speed that the alternating current alternates. I don't have as much control, but that also works. So here's another picture. Often what we do is we use a solenoid inside the motor. We use that as well to turn. So the split metal cylinder on the armature is called a split ring commutator. Current direction is from the brush at A to the left half of the commutator, then to the coil of the wire on the armature. The armature is the thing that spins. We call that the armature, the loop of wire. Oh, and by the way, how do I make the motor stronger? Instead of one loop of wire, let's have hundreds of loops of wire. Yeah, you want to double the strength? 2 loops. You want to make the motor 100 times stronger? 100 loops. And so that's why we often use a solenoid, many, many loops of wire. Electric, I'm just going to read here. Electric motors come in all sizes. Some are very tiny. They drive little toys. Others are huge, drive trains or buses or cars. You'll find electric motors in toy trains, cars, clocks. That's an electric motor in my wall clock. Wheelchairs, streetcars, can openers, cement mixers, furnace fans, robots, many other devices. The motor that I showed you only operates on direct current. Alternating current motors work on essentially the same principle, but you don't need the split ring commutator because the current is already alternating. You've got something that's flipping the current for you automatically. Well, thank you very much. That just works quite nicely. What's your homework? Number 9, number 13, and number 14, and number 15, and number 17. Every question and the take-home quiz. Other cool applications. Believe it or not, you can make a shrink ray.